Okay, so one more time with chapter 13, vector functions. This is part 2 of arc length and curvature. Okay, so we are going to introduce two vectors known as the normal and the binormal vectors. So as seen in figure 6, at any point along a curve, there are going to be many vectors that are orthogonal to the unit tangent vector. We're going to start with 1. Because we know that the magnitude of t of t is equal to 1, we know that t of t is perpendicular or orthogonal to the derivative of t of t, which means that the dot product between t of t and t prime of t is equal to 0. So we are going to define what we are the unit normal vector, or the principal unit normal vector, as n of t is t prime of t over t, the magnitude of t prime of t. This then gives us a unit vector, and this vector points in the direction the curve is turning. It is pointing into the concave portion of the curve. So as your curve, sketch it here, as your curve is this way, the unit normal vector is going to point this. As the curve goes this direction, the unit normal vector will point into the concavity of the curve. We also are going to define b of t, which is the binormal vector, and it is going to be the cross product of t of t and n of t. This is also a unit vector. We know that because b of t is a cross product, b of t is perpendicular to t of t, and b of t is also perpendicular to n of t. Okay, so these three vectors form what we are going to call the t and b frame. So if this is our unit tangent vector and our unit normal vector, which is perpendicular, and then this is our binormal vector, which is also perpendicular. This forms what we've known as the T and B frame. And as you can see in figure 7, you can see that T and B frame is rotating and moving as the curve is turning. This plays an important role in differential geometry and then in its applications to spacecraft. So the plane that's formed by the B and the N vectors at a point P, this is called our normal plane. So this is our normal plane. And it is all lines that are orthogonal to the tangent vector t. The plane formed by t and n are called your osculating plane. So let's do an example here. So given r of t is cosine ti plus sine tj plus tk, we know so we're going to find the unit normal and the unit binormal vectors. So we know that r prime of t, which we have found previously, is going to be negative sine t, cosine t, and 1. The magnitude of r prime of t we found was the square root of 2. We found that our unit tangent vector is going to be 1 over the square root of 2, negative sine t, cosine t, and 1. Because remember, t of t is r prime of t over the magnitude of r prime of t. And so now we need t prime of t, which is going to be 1 over square root of 2. It's going to be negative cosine t negative sine t, and 0. So now let's find our unit normal vector, which is going to be t prime of t over the magnitude of t prime of t here. So n of t is going to be 1 over square root of 2, negative cosine t, negative sine t, and 0, over 1 over square root of 2, which gives us simply negative cosine t, negative sine t, and 0 as our unit normal vector. And so what we can see is that the unit normal vector at any point on the helix is going to be horizontal, and it points towards the z-axis. So our binormal vector is going to be the cross product of t of t and n of t. So setting up our matrix, t of t is 1 over square root of 2, negative sine t, 1 over square root of 2 cosine t, and 1 over square root of 2. Our n of t was negative cosine t, negative sine t, and 0. Okay, so our I component is going to be, this is going to be 1 over square root of 2 sine t. J component is going to be negative 1 over square root of 2 cosine t. And then our k component is going to be 1 over square root of 2 sine squared t plus 1 over square root of 2 cosine squared t. And so we can see that our binormal vector is going to be written as 1 over square root of 2 sine t minus cosine t and 1. Okay, so since we have curvature, which we defined as dt ds, and curvature at a point indicates how tightly that curve bends. Since t is a normal vector for the normal plane, dt ds tells us how that normal plane changes as p moves along the curve. Note that the vector, this vector, is going to be parallel to our normal vector, and we will prove that in class. So as a point moves along the curve, the tangent vector at p is going to rotate in the direction of the normal curve. And the space curve can also lift or twist out of the osculating plane. Since our binormal vector is normal to the osculating plane, if we had dB ds is going to give us information about how the osculating plane changes. Gives information on how the osculating plane changes as the point moves along the curve. So we know that dB ds, because it is parallel to n, we can then define, there's a scalar that we're going to define then as our torsion. Torsion is a scalar and defined as the dot product of negative dB ds dotted with the normal vector. It's going to be easier to compute if it's expressed in terms of the parameter t instead of s, so we're going to, similar to the way we dealt with curvature, we're going to define torsion then as the dot product of b of t, b prime of t dot n of t over r prime of t. Intuitively, torsion at a point on a curve is a measure of how much the curve twists. So measure of how much the curve twists. If your torsion is positive, the curve is twisting out of the osculating plane at the point in the direction of the binormal vector. If the torsion is negative, the curve twists then in the opposite direction. Missing the rest of this curve, so R of t is, this is our helix that we've been working with, cosine t, sine t, and t. So we know that you have ds dt, which is the magnitude of r prime of t, was the square root of 2. You had n of t is negative cosine t, negative sine t, 0. We had our binormal vector as 1 over square root of 2. Apologize, that's sine t. Negative cosine t, 1. We can then find b prime of t, which is going to be 1 over square root of 2 cosine t, sine t, 0. Okay, so now we're going to calculate our torsion, which is negative b prime of t dot n of t over the magnitude of r prime of t. And so we have b prime of t is 1 over square root of 2, and then we are multiplying negative out here, so this is negative cosine squared t. Sine t minus times negative sine t is negative sine squared t, and then we have 0, and the magnitude of r prime of t is the square root of 2. And so we are left with, this simplifies, we have negative 1 over square root of 2 times a negative 1 over square root of 2, and that simplifies to simply 1/2. So figure 13 shows that we have a circle in the xy plane with curvature 1 and torsion 0, because the b prime of t and n of t, that dot product is 0 because those are orthogonal to each other. In figure 14, this is our helix, and we found that the curvature of that helix was 1/2, and our torsion is also 1/2. So both curves have constant curvature, but the circle is going to have torsion 0, whereas the helix is going to have constant torsion of 1/2. And so we can think of the circle as bending at each point, but never twisting. Well, the helix both bends and twists upward at each point. So it can be shown that under certain conditions, the shape of a space curve is completely determined by the values of curvature and torsion at each point on the curve. And then we have one last formula that we can use for torsion. And so torsion is going to be the magnitude of r prime of t cross r double prime of t dotted with r triple prime of t over the magnitude of r prime of t cross r double prime of t. And I'm going to go back quantity squared. I'm going to go back and add all my little vector notations in here. So we will spend some time in class working through all of these, because I know there's a lot of new terms and new words in here.